All right, so hello and welcome back, everyone. We are continuing our discussion on motivic homotopy, and right now, by the last class, we already discussed the Coulomb model structures. These are nice structures that encode homotopy theory for arbitrary categories. We did see that how what is the model structure on topological spaces are, which was very natural. We did briefly mention the homotopy theory of simplicial sets. Today we will focus more solely on homotopy theory on simplicial sets, and let's see the model structure on them. So let us begin. So to define a model structure on any arbitrary category, we need three things. We need the category itself, we need the map cofibrations, the map fibrations, and then we need our weak equivalences, satisfying some axioms, some criteria in between them. And we did see how to define homotopy category there. We did see what are the different relationship between defining different homotopy categories, and these are all isomorphic. Today, your category is your simplicial set. Now let's talk about what these maps would be for simplicial sets. Let's start with the easy ones, weak equivalences. So this is your map between two simplicial sets, right? And I want to define weak equivalence for these guys. For that, note that I have geometric realization from simplicial set to topological space. Apply geometric realization, and I will end up with this guys. Now, the thing is that I will asking whether this map, a map between two topological spaces is a weak equivalence, weak homotopy equivalence makes sense. So we do have a inbuilt default weak homotopy equivalence here. We saw it last time. It turns out our choice of the definition should be or would be that I call this map a weak equivalence if this guy is a weak homotopy equivalence, their geometry realization. That is the first thing. The second notion is your cofibration. Now, we did talk about how to build these cofibrations for topological spaces itself. So remember how we did for topological spaces. For topological spaces, your cofibrations were lift to your trivial Serre fibration, right? And whether or not that trivial, we did mention this fact about topological spaces, the cofibration on topological spaces, that it's cofibrantly generated. That means I can define a generating self set for trivial cofibrations and fibrations. Trivial cofibration and cofibrations. That was your I cell or I injective maps. Cell maps. You declare all of these guys from the delta of dn to the delta n as your trivial cofibrations, right? And we look at all their push outs, retracts, and wait, this guy was trivial cofibration or cofibration? Um, yeah, no, this was your cofibration, I guess, yes, right? Yep. and we look at all their push outs, retracts to get to get our uh, all our cofibrations, right? We will do something similar here for cofibration here. So for topological spaces, a big thing is that not all maps are, not all injections are cofibrations. But for simplicial set, if you look at an injection between two simplicial set, call them, I don't know, K to L, it's an injective map in simplicial sets. Injection in simplicial set. Inclusion is called inclusion. Then it can be looked at as a chain of smaller simplicial sets, a chain of simplicial sets. Let's write them down. This is your the co-limit of AIs, which will be your union in this case, and that will turn out to be your L. There exists this chain. And what is this K0, K1? That you get by attaching cells. Looking at this push out diagram. This is how you get KIs. And I'm saying that these guys exist for all inclusion of simplicial set. You believe that, you take this as a lemma. That means if you declare these guys to be cofibrations, define. Then by taking your cofibrant generation, you'll end up saying that any inclusion map between K to L is a cofibration. Because push-outs are closed under cofibrations are closed under push-outs. Are we happy with this so far? Are you guys good? Following?
Yeah. Well, what is the union taking from? You have disjoint union. What is this disjoint union is taken? Oh,
Yeah, disjoint union, like there exists some collection such that you can write them down.
yeah.
So call this J, I guess. J.
Mm.
Yeah. There exists the collection as well, this J collection as well. This J also comes with an existence over here. So this is how you get your cofibration. So to know all the cofibrations, it's enough to focus on this guy. This is the motto here. Most why we talk about this, because most model categories that we'll care about or we'll see will be cofibrantly generated. That means that I can give you this generation set. So this is we'll know all the cofibration if we just know this. Focus on this. Cool. That means that, okay, I did not define what trivial fibration is, but that means that by using your lifting properties, you can get all your trivial fibration by looking at lifting with respect to these sets. to get all your trivial fibrations, right? So what do I mean by that? So your map x to y is a trivial fibration if and only if I have a lifting with respect to these guys.
These
Okay?
are co-fibrations.
Yeah, these are all co-fibrations, yes.
You are writing fibrations, right?
Did I write co-fibration? No, these are co-fibrations.
The blue line, the very bottom
Okay.
blue line.
So
No, look at all the lifting with respect to these to get all your trivial fibrations.
Okay, to get. Okay, that's okay. I see what you mean.
Yeah. So what I mean here is this diagram here down below. That's all I mean. Cool. Now, let's look at the next feature of your model categories, that any map, the factorization thing. So any map x to y f is a map between two simplicial sets. It should factor like this, right? By some z. This is your entire map f followed by a cofibration.
oh, by
This
the
should
way,
happen. Yeah.
yeah, do you solve the factorial problem?
Yeah. You have to take functoriality in the assumption. Yeah.
Well, assumption, right? Not a property. Okay,
It's
thanks.
yeah, you have to take that out. Otherwise, we did talk about this, I think, yeah. Because otherwise you want the cofiber replacement to be a weak natural transformation. You want this a weak natural transformation from your cofiber replacement to your identity morphism on the model category, right? So what do I mean by that? So you're here to here A and call this phi to B, A to B map F. Now this map will split in between by some QA. Boom, boom. This is your QB. This map won't exist. This blue map won't exist if you do not assume your factorizations to be functorial, right? So you need to take functoriality into consideration. Yes. Yeah, do you have a comment?
No, this map always exists, but it might not be commutative.
Sorry, yeah. This map might not give you a commutativity with respect to these diagrams, right? This map will always exist by QAs, right? Otherwise, the commutativity is guaranteed by your functorial factorization. Yeah. Now let's look at how do we get this for simplicial set. This should be the case. To give a model structure, this should be the case. The factorization. Now to get this, we build this step by step. First look at all the diagrams D1 for which you have that look like this. They commute with respect to this. Note that this diagram doesn't have to be pushed out because this is your cofibration. So I'm trying to get a cofibration from X to Z. The idea is to build this Z and then show that the map out of the Z is a fibration, trivial fibration. How do we build this Z? By attaching cells. Try to get closest to Y. That's the idea here. So even though this diagram is not a push-out diagram, we take all possible, for those for which this diagram commute, we take all possible push-outs, with respect to that. This is not a push out. So this is the idea. Keeping this idea in mind, let's look at the push out with respect to these D1 diagrams. That will be bum, 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 bum. Yeah, delta. This is your push out. Call the push out as your x1. Now this guy is your inclusion, where this D is varying. D is varying on this D1, on this diagram for which this Y is commutative. Now this will factor through your, okay, let's draw it a better way. Your Y, this outer diagram is commutative because it's a part of the diagram in D1, and this is your F map. And by the universal property, you get this map. Let's draw a different color for that. This is how you get the X1. Now you iterate this process. You will iterate this to get X2. What do I mean by that? You look at all those diagrams D2 for which you have this commutative diagram. Delta Dn, delta n. This is your X1, this is your Y, and this is the map, the universal map that you get there. Look at all these D2 diagrams and construct X2 in the similar fashion. So now your X2 will be pushed out of these diagrams. Boom. And then again, using the universal property, you will get this map X2 to Y, because you will have, yeah, again, the blue. I should have used a different color. You have the blue map by the universal property here, and by the commutativity of the diagram D2, so you have these maps here. This is also your D belongs to D2. You attach cells to get to X2. You keep iterating this process, so you will have a chain of maps. X1, X1 goes to X2, and all of these maps are cofibrations. X2 is included in X3, so on and so forth. You defined this new set. Now this Z that I have written here, this Z guy is your co-limit of these xi's, which is basically your union in this case. That's all. All we have left is to show that Z2, this Y map, this Z2 Y map, yeah, this guy is a fibration, because, right, because we already discussed this in the last class that co-limits, we don't need this, but yeah, X is included in your Z, so it has to be your cofibration in this category. But even it was not the case if it was like a chain of cofibrations, and we take their co-limit, and the map will still be a cofibration. Anyway, all you have to show is this. Now we have boiled down the problem to show this guy. For this, we need to introduce something called as small object and small object arguments. So let's look at that. Yeah. So what is your small object argument? Small object argument tells you that if I have a filtered, so it tells you essentially, this is the slogan, filtered colimits commutes with finite limit. So what does that essentially tells our co-limit? I think, yeah, it should be co-limit. We'll see what this is, but co-limit or limit, let's write down the statement first. So if you have a chain of filtration, chain of maps like this, sequential sequence of maps, and you look at its co-limit, co-limit of xi, and take an object A in the home, whatever the home is in that category, this guy, and you look at this guy as well, A to xi, and take its co-limit or limit. I'm a little bit confused here. Co-limit of the home sets over here. Yeah, the home.
Are you taking
Yeah,
limit?
since this is since this is contravariant position, we have to take the limit, I think. Yeah, go ahead.
Yeah, I'm just saying maybe it's taking limit.
Yeah, I think we are taking the limit because it's a contravariant map, right? So that means we are taking the limit here. So these may not be in bijection. If they are in bijection, we call that A satisfies small object argument. And the object A will be called small object. So this relation over here, this may not hold, but it will hold for small objects. What does that mean? That means that if you have a chain of maps, so yeah, so if you have a map A who goes to your co-limit of xi, let's draw the picture over there. That is your A, oh no, I can draw it here. A x0, x1. This is your co-limit of xi, and I have a map, boom, over here. It should be equal to the limit of these maps A to xi. That means this A to xi has to factor through some xm. That's what it means. That's what it means, right? A to xi, all these maps. So now A to xi, x0, x1, x2, xm, I may not have maps, but when the maps, like you know this fact, right? For your sequence of co-limits, even if you ignore first a few maps, it won't affect the co-limit itself. Now that means that it will factor through some xn. Is this clear?
Sometimes called compact object in derived category. So yeah, maybe small is fine. Yeah, I usually heard it's called compact.
Yeah, it is also called a compact object. Yep. Sometimes it's also called a compact object. Yeah. I think compact is more reserved for homotopy colimits. That's where I have seen that. But
Nice.
Anyway, let's call this small. So it has to factor through some xm. Now, how does this help? Using this, we can prove this argument over here. Let's add a page in between. Now, I want to show that this Z2 Y is a trivial fibration. This is what I want to show. For that, we already concluded it is enough to get these maps, lifting with respect to these maps. Boom, boom. I want a lift here. Okay. Now Z is your co-limit. This is your co-limit of these xi's. Then it means that it factors through this map over here, delta of to n to some xm over delta n. This is delta into, this is your delta into y. Let me see if I'm drawing this diagram correctly. This is your delta into y, and no, I'm not drawing. Okay, we have to be a little bit more smart here. This is your xm. This is your xm plus 1. Yep. This is your arrow coming from over here. This is the z from xm to z. This is how it factors through. This is, so delta into z, this entire thing is this entire thing. Essentially, that information over there is same as this information over here. And from z to y, you have these maps. This is your inclusion map. This is z to y. This is the map that I want to show as our fibration, trivial fibration, and delta into y, we have the map by the commutativity of the diagram. Now, yeah, let's see. Now to get the no, I think we are done now, right? Yeah, we have found the lift. This is our lift. Such that the diagram commutes.
Where do you use the small object property?
To get this xm over here.
Okay.
Yeah. To get the fact that this map over here, this delta into z, is same as saying this delta is same as this map f, is same as this map f over here. Now, to get a map from over here to here, yeah, this is the map that we are looking for, and that map came from, yeah, looking at this inclusion xm going to xm plus 1. Yeah. So this helps, right? So we are done with the, we show that it will factor through at least one of the factorization is done. Okay, let's move on to the next topic then. Now we look at a feature of simplicial sets that's generally called model category being tensored and co-tensored. So this is the feature. The feature is, if you have these maps, A to B, a cofibration map, and X to Y is a fibration map. This is also a map of fibration. And you look at the pullback diagram of this guy. So you apply SY here, simplicial set, all the map from the simplicial set maps from over here to here. Oh, I think you don't apply this, you apply this guy S bar over here. Yep. The closed simplicial set map. So this guy will give you a map from S bar to, it's a contravariant map, so it will flip the arrows. And from here, if you apply the map S bar A comma, this is a covariant map, so it will preserve the arrows, giving you this map. It makes sense to take a pullback of this diagram, so let's draw it. Pullback of this diagram will be your S bar A comma X, S bar comma Y, S bar b comma y. Boom, boom. This is your pullback. Now we have maps from this object. Is part of b comma x. Yeah, by applying contravariant x on this guy, you get this map. By applying covariant b on this guy, yeah, you get this map. That means by universal property of pullbacks, you get this map, right? So far we haven't concluded. This diagram always exists. Now when A to B is your cofibration and X to Y is your uh, for fibration, then this map will be a fibration. This is the claim. Moreover, if one of them is a trivial fibration or trivial cofibration, by one of them I mean either A to B or X to Y. If any of them is a trivial fibration or cofibration, then this map, this universal map, is also trivial. Yeah, and given this as your in your assumption, like I think you can analogously prove the push out version here. So uh, I've I forgot what the push out version was. I think both of the map has to be fibration, and then you take the push outs and you show that the map out of the push outs is also a it will be a co-fibration in that case, and will be a trivial co-fibration if and only if one of them is a trivial co-fibration is a weak equivalence. However, we don't need that for simplicial sets because we are trying to get some features out of your fibration. So this is good enough. Now we'll prove this. But only when we'll prove this for when A is your initial object and your Y is your terminal object. And I will give you the idea of if you understand the proof here, you will understand like how to generalize that. But we'll use only these cases, so it's sufficient enough to prove that. Proof for these cases for these two cases. So let's do that. So how the diagram would be now, if your Y is your trivial, that means that all your objects on this corner, they are basically points, pointed like a point simplicial set, called like trivial simplicial set, and their pullback will also be a point. Now the map is Bx, boom, S bar Bx would be essentially this guy, a map into the point. I want to show this S bar Bx to this guy is a trivial fibration. Sorry, to show fibration. That means that I have to get liftings with respect to, okay, we can't use x anymore. We have to use some different notation. For these guys, I want to find a lift. I want this lift. This is what you want, right? How do we get this? For that, we look at the, so we did this in the in our first lecture, that we have something called we can define smash product here, and the smash product with respect to this set is 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 adjunct to your this S bar, this internal home thing. right? Using that fact, I can translate this picture, this diagram, into this diagram. In fact, we don't need to use smash here because we are not talking about pointed simplicial set. We can't talk about smash here actually. We take the product. Even better. Same argument will work for. So if you replace this S bar by S bar star, same thing will work. Everything will work. So L cross B to Y. Boom. Oh, not Y. Point. Getting a lift on the left-hand side diagram is the same as saying getting the lift on the right-hand side diagram, right? Now, K to L is an inclusion. That means that K cross B to L cross B, this is also an inclusion, right? And it is also an weak equivalence because, yeah, this is, we're assuming this is a weak equivalence to get the lift, right? To show that it's a vibration. This will also be a weak equivalence because your geometric realization of this guy is this guy. Now K2L is weakly homotopy equivalent. That means that K cross B is weak homotopy equivalent to L cross B, for which you get this weak equivalence over here. Now we started with X2 Y. Y is a point here. This map being a vibration. That means that this guy is a vibration, for which you get this lift, and that will give you this lift over here. And you show that it's a vibration. Are you happy with the argument? Hello?
Why K cross B is weak equivalent to L cross B?
Yeah, so you started with the so what you're trying to do for all the trivial cofibrations, I'm trying to get a lift, right? So you start with K to L being a trivial cofibration. It's an injection and a weak equivalence. That means that it induces weak homotopy equivalence on their geometrically realized topological spaces. This is by definition. Now, this is a feature of geometry realization. They preserve products. Okay. Now here to here, you'll have these maps. This is your weak homotopy equivalent. Because K to L is a weak homotopy equivalence, you get this. That means that your boom, this has to be a weak homotopy equivalence now. That answers your question, right?
Yeah, thanks.
Thanks. Now that will give you things. That will give you that this is a vibration. And by the way, if this guy is a trivial vibration, this x to this guy is a trivial vibration, that means that it is enough to show that lifting with respect to these guys. Okay, let's copy the diagram over here. Yeah. Copy the diagram over here, erase this vibration map, erase this trivial vibration map. Now, this guy is your trivial vibration. That means that you get the map here. And that means by same argument, you will have the map with respect to all the cofibrations. That means that it's a trivial vibration. Yeah. So all this argument is also true for your pointed simplicial sets. And I said that analogously you prove the general argument. is nothing but using your product and this internal home of simplicial sets are being adjunct. So you can reiterate the same argument generally to get this. So there's nothing fancy going on over there. Yeah. Um, yep. So that concludes it. Now using this, we prove the Whitehead lemma for simplicial sets. What was the Whitehead lemma for arbitrary model categories? It was that if A to B is a map between two bifibrant object, so A and B is your bifibrant, then if this is a weak homotopy equivalence, that means that it's an actual homotopy equivalence. That was your that was your Whitehead lemma. We mentioned it in the last lecture. Note that all objects, all simplicial sets are cofibrant. You'll always have an inclusion of the empty simplicial set to any simplicial set, right? And this is an inclusion. So it will always be any object in the simplicial sets will be your cofibrant object. It is enough to state the Whitehead lemma for simplicial set as this, like if A and B both are fibrant, then now that I'm talking about this, I just realized I did not talk about fibrations for simplicial sets. So I think it will be wise to talk about the fibration. Yeah, I messed up my notes somehow. But yeah, let's talk about fibration for a while and then we'll talk about this. So A to B, if both of these are fibrant, A and B both are fibrant, and it's a weak equivalence, then we have a homotopy equivalence. A to B. This is what we will show after we talk about fibrations, which I don't think I wrote down in my notes. Okay. Okay, let's talk. We should have talked about fibration before talking about this. Okay, let's talk about fibration here because I did use this guy to be a fibration without defining it. So let's set up a page here and talk about fibrations. Sorry for missing it out. So you already defined our trivial fibrations as lifting with respect to these guys, right? This is your this is your cofibration. So all your trivial fibrations will be this, the lifting with respect to these guys. Now, how do we define your in general fibrations? So for that, we need to look at something called as horn of a simplicial set. How does this look like? So this essentially means you are looking at your your simplicial set without that kth, not without that kth vertex. You are taking out the phase that is opposite to your kth vertex. Let me give you a picture of this and that will be more clear. 2, 0, 1, 2. This is your delta. This is a horn of, this is your zeroth horn of your 2 simplex. And this is your standard 2 simplex. This is an inclusion, but this is your standard 2 simplex. Yeah. So 0, 1, and 2. Now for, in your topological counterpart, in your topological counterpart, this kth horn will always be homotopy equivalent to these guys, the actual simplex. That means if I take the geometrical counterpart of simplicial sets, we'll always have this lifting. There is no way you can say that this diagram will translate into something like this. We'll have the commutative diagram, but we do not know the diagram, we will get the lift or not. And we impose this lifting condition to be our for choosing our fibration. Note that this will always be your trivial cofibrations. This is your always trivial cofibrations. And if this lift exists, this blue arrow exists, then I will call this x to y the fibration. Yeah. Now, if for your topological spaces, this was your J set. This dn cross 0 to dn cross I. This was your J set, right? We declare this guy to be your trivial cofibrations, J cells. And we by taking the iterated push outs and iterated and taking their retracts, we got all our trivial fibrations. We are doing something like that over here for simplicial sets. These are also called Kahn fibrations. And Kahn came up with a brilliant idea of getting given any simplicial set to get the fibrant object. We'll see that. But before that, let's get to our lemma. So we want to show that this is actually a weak homotopy equivalence between two fibrant objects. Is actually a fibrant object. Oh, sorry, is it actually a strong homotopy equivalence? How do we show that? So for that, your A to B is your weak homotopy equivalence by your factorization principle. You have this map A, B, C. One of them has to be trivial fibration or trivial cofibration, that by 2 out of 3 property that will tell you the other one is also a trivial cofibration. Now, if I get homotopy inverse from here to here and from here to here, we'll be done. So it is enough to state this theorem. This is if I get homotopy inverse. Will be done. So that means that it is enough to state the theorem for trivial cofibration when A to B is your trivial fibration and A to B is your trivial cofibration. Now let's assume the case 1 first. A to B is your trivial fibration. And A and B both are your fibrant object. That means that this is also a fibration over here. We don't need this to be fibration, to be honest, but whatever. This is also a fibration. Map is good enough in this case. Yeah, I think this will be better. Yeah. We want the lifting from B to A. Boom. This is your inclusion map, a trivial cofibration. That means that it has lifting. We have this lifting over here. Oh, we don't know it's different co-vibration. We only know it's a co-vibration. Yeah. We have the lifting here. Call this lift as your S. Now, by definition, your F compose is identity or B. If we can show that your S compose F is identity on A, we'll be done. Or not identity, homotopy to identity. For that, let's recall the notion of homotopy for simplicial sets. To map from X to Y, your F and G are called homotopic if this happens, right? Your X to X, X cross delta 1 to your Y. This is your F comma G map. Call this map H. And this is your, yeah, this is your, I don't know, I0, I1. We call F and G are homotopic. F is homotopic to G if there exists H for which this diagram commutes. Right? If you recall the notion of homotopy here. So we want to find out A to your over here. This is your I no, it's fine. A to A. This is your A, and this is your S F to your give me 1 second. Let me see. Let me write this. Let me write this down. First, A to your A cross delta 1. Yeah, this is your SF co-product with your identity A. Yes, if this diagram commutes or not, if there exists a H for which this diagram commutes or not. This is your H. This is what you are trying to find out. Is it clear what you're trying to find out? This H? Are you on the same page? Because I talked so much.
You're fine. Yeah.
You're fine? Okay, go. Let's go. So we want to find this guy out. For that, we have this map A to B. This is your F map. And we have this guy A to A cross delta 1 to B. Yeah, let's remove this guy. This is the map out of your co-product. So this map exists. This is your A to B F map. What is this map? A cross delta 1 to B. Um, hmm, let's see. Yeah, this map is your. Yeah, we have to do a convoluted way for this. This is your. Okay. We have the map A cross delta we have the map A to B over here. Now A cross delta 1 to A, we can take this map by like projecting everything on the A component, right? And that thing will give me the map over here. Yes. This is your F compose with projection of A. Nothing fancy. So this diagram is a commutative diagram, right? And this is your inclusion. This is your inclusion. Now x to y is we have A to B, we have assumed that to be a trivial fibration over here. No, A to B we have assumed to be we are only on this case, so we assume that to be your trivial fibration over here. Then it means that this is you get to choose this to be a trivial fibration, and then we get this left over here. This is the homotopy that we are looking for. Are you happy?
What is the map on top? How can you take the disjoint union of two maps?
It is the co-product. It is the co-product map. So, this is your A. This is your this is your empty set. This is your A to A. It's a co-product. Now, there are two ways to go to A. One is your SF, and there is identity. Boom. That will induce the map, right? SF compo, SF and identity. That's that map out of the co-product. Good. Now, this is your first case. The second case is to show that when this guy A to B is a trivial cofibration, then for that the lift will exist. And this is where we'll use the fact that it's a fibrant object. So A to B, this is your weak homotopy equivalence. This is your call this A. By A being fibrant, I have this guy. Damn. This as a fibration. Then that means that if I compose this guy P with A to B F map, now P compose F is your identity. Now he's showing the exact opposite. Now we are trying to find F compose P is homotopic to identity. You want to show that. That means I want a diagram like this to commute. Sorry. This is your B to A. Yeah, so B disjoint union B to P cross delta 1 to boom 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 to P to B. Identity on B. So this is your F compose P, identity on B, and this is your inclusion map over here. So this is a cofibration. I want to find this H over here. That's the game. Now to see this, we split this map through this object. So first of all, we can embed this diagram inside over here. Y to start. Being a cofibrant object, I always have this cofibration from B to start. This is the part we're using, by the way. This is the part where we use the fact A and B being fibrant. So this is a vibration. This guy is not a trivial vibration, trivial co-vibration, but however, we can split this map through a trivial co-vibration. So this is this map. Think of this as your double mapping cylinder. Yep, double mapping cylinder. This is called this is literally your co-fiber replacement over here. So this is your B cross delta B cross delta 1. Yeah, this is your weak homotopy equivalence, and this guy is also a co-fibration. Here to here, this guy is a co-fibration. From here we'll have, yeah, you will have the we have to write that map down, but we will have the map out of the push out. So this is your the map over here to B. This is your co-fibration now, and we have this map commuting. We have this lift over here. That means that if you ignore this part, even if you ignore this part, we'll have the required lift, required H. Are you happy with this or not? Are you on the same page, or do you want me to repeat it again, or like? Okay, he's showing thumbs up. Professor Wong, you're also happy with this? Okay,
Yeah, I'm fine.
yeah. That means that we have proved our Whitehead theorem for simplicial sets. Now, all it boils down to, the slogan here is to map between two fibrant objects. All our objects are co-fibrant, but we do not know if in fact, we know this, not all the objects here have to be fibrant for simplicial sets. Now, that's a problem for defining your homotopy groups, right? Because we define the homotopy groups in the following manner. So what do we need for the notion of homotopy? We mentioned this, the map between your co-fibrant object to your fibrant object. These maps, these homotopy, these equivalence maps, for these your homotopy, left homotopy and right homotopy coincide. If this guy is your co-fibrant and this guy is your fibrant, then homotopy makes sense. In topological spaces, your X may not always be co-fibrant, but your Y is always fibrant. That's why you can define your homotopy groups that easily for topological spaces. Your Y is always fibrant. And remember how we define. We define the homotopy groups as your X, Q to X and take their homotopy classes. This makes sense because your sphere is a cofibrant object. Right? All of this makes sense for topological spaces. But the problem here for simplicial sets, this Y may not be fibrant. And hence the following definition. For fibrant Y, you can define your your qth homotopy group by q of y as your looking at yeah looking at all your homotopies between qth simplicial sphere to y. Now we don't have to worry about SQ being cofibrant because all your simplicial set will be cofibrant, but for fibrant y this makes sense. And this is also an, I don't know if this is an exercise or not. I think this can be an exercise to show that your pi q of x is same as isomorphic to your pi q of geometry after taking the geometry realization. These two notions coincide. Now, how do we also since we are talking about homotopy groups, these homotopy groups behave exactly similar to your topological spaces. What does that mean? For your homotopy pullbacks or pullbacks of our fibrations. So if you take F2B, this is your fibration, and take its pullback. Or in general, if you take homotopy pullback of any map, call this map A, you'll get a long exact sequence in terms of homotopy groups in simplicial sets. In general, like you will get Maillard-Vittori sequence for if this is your non-trivial. If this guy is your non-trivial, a I don't know. Yeah, let's see. If this is your G, this is your B, this is your fibration, then you will get a Maillard-Vittori sequence. The point is, even if these simplicial sets, these the definitions of homotopy groups on simplicial sets is fibrant, even though it is limited on only on fibrants. If we define the homotopy groups, they behave exactly the same as your actual homotopy groups by these properties. Okay. Now, this is I will end this talk by just by mentioning this, that given any object, you can build a fibrant object given any simplicial set. You can get a fibrant set, fibrant simplicial set. This resolves all our problem. This resolve will all our problem. Now I can define the homotopy group of this pi qx as your pi naught of this is not of is of your qth dimensional sphere after replacing the simplicial set with this fibrant replacement. If I define like this, it will solve all our issues. We solve the fibrant issue. And kudos to Khan, this is exactly what he did. So Khan introduced this EX infinity functor. This is looking at, given a simplicial set, you look at all possible all the subdivisions of them. And then the co-limit of them, it will be a simplicial set and it will be a fibrant object. What do I mean by that? So let me show you by simple example. For that, we need to define something called as subdivision of your standard simplex. Let's look at it. Let's look at through example instead of giving you the definition. So for how does delta 1 look like? This is your 0 and this is your 1. A subdivision is exactly how it sounds like. It's your normal barycentric subdivision. So this is your 0, 1. Splitting through here. Right? So if you want to look at in terms of your maps in your simplicial set maps, it will be your delta 1, two-way of including delta 0 with your D0 map with your D1 map. How does delta 2 looks like? Delta 2 will be your 0, then 1, then 2. Okay, 0, 1, 2. Then your barycentric subdivision, this is your 0, 1. This is where you go to 0, 2. This is where you do 1, 2. And this is the subdivision 0, 1, 2. Boom, boom, boom. So subdivision, this is your subdivision complex. This is your ST delta 1. This is your ST delta 2, and so on and so forth. So this is essentially your barycentric subdivision. So Kant said, look at the simplicials instead of looking at, map from delta n to your delta n to x. You look at the map from the subdivision of delta n to x and keep looking. Give it a name. These are simplicial set maps. Hom simplicial set. EX, EXXN. Yeah. And keep looking. So you will have the chain of these guys. X goes to EX of X, then EX square, EX of X. Let's like this term. And take its co-limit. So introduce this infinite simplicials and keep taking their subdivision after subdivision after subdivision. And you will get something called at co-limit of this guy, co-limit of this EX of X over N. He called this EX infinity of X. And boom, this EX infinity is a fibrant object. So shout out to Kant. And this is a good place to stop.